Hello, hello. This video will be going over Edmentum Algebra 1, Semester B, Unit 6. The section we'll be going over will be Factoring Polynomials, Part 1. There's Part 1 and a Part 2. This video will just be covering the Part 1 tutorial. Before we get into the section, let's understand what factoring means in general. So to factor something means to break it up via multiplication. So if I were to factor a number, say 10, I would break it up via multiplication into its separate parts. So I could say I factor 10 into 1 and 10, because 1 times 10 is equal to 10. Or more meaningfully, I could also break it up into 2 and 5. So I have factored 10, and these are the factors of 10. 1, 2, 5, and 10 are the factors of 10. If I had, say, a variable like x squared, of course we know that an exponent means that you multiply the base as many times as the exponent tells you to. So if I were to factor x via multiplication, I would get x and x, because x times x is equal to x squared. So that is factoring in general, but it's going to get much more complicated when we're trying to factor polynomials. But go ahead and keep that idea in your head, that factoring means to break something up via multiplication. So we start on page 5, where we encounter our first warm-up question, where it says, select all the correct answers. Which three expressions are equivalent to the expression 3x minus 12 minus 2 times x plus 12? So we are not necessarily getting one answer. We're not just simplifying, but we are trying to see how we could rewrite this equation without changing its value. So let's play around with it and see what we could find. We're looking for three equivalent expressions. So off the bat, it looks like we could distribute this back end of the expression. So that would be negative 2 times x plus 12. So we distribute the negative 2. Negative 2 times x would be negative 2x. And then negative 2 times 12 would be minus 24. And the rest would drop. So that would be 3x minus 12 minus 2x minus 24. Which, let's see, 3x. I thought we would have gotten this, but that's a plus 24 versus our minus 24. So this one is actually not going to be one of our answers. Let's see, did we have an equivalent? No, it doesn't look like. Well, let's go ahead and see if we can simplify at least. So we have 3x minus 2x, which leaves us with x, and negative 12 minus 24, which would give us negative 36. Okay, so this wasn't all for naught, because this is one of our answers when we completely simplify it. Okay, so distributing didn't give us more options. Let's see about going the other way with factoring. So we look at this first part of the expression, and the way that we start to factor something is by isolating it and ask ourselves, do these two terms have anything in common via multiplication? Because, of course, factoring has to do with multiplication. And if you study this for a moment, it looks like they both have a 3. These are both multiples of 3. So by factoring, I could take out a 3 from both. So that means I'm dividing out a 3 and putting on the outside. So I'm separating the 3 from these two terms. So 3x divided by 3 is going to be x. And negative 12 divided by 3 is going to be minus 4. And of course, we drop the rest of the expression, minus 2x plus 12. And let's see if we find anything here. It seems that we have this. So now we're looking for our other one. This does not simplify into that. This does not simplify into this. So our last potential option is here. And if you remember, when we distributed this side, we got, just rewriting this part, when we distribute this, we know we got negative 2x minus 24. So this one is going to be our final option. So let's go ahead and get this mess out of the way and select our 3 answers. So let's be 1, 2, and 3. And it seems we were correct. Moving on. So next we come to page 12, where we hit our lesson activity, where it goes over distributing factors. So this is kind of a retread of the last section, which had to do with multiplying polynomials. So if we were comfortable with that section, we should very much be comfortable with this one. But let's get straight into it. So it says, Part A, simplify x plus 2 times x plus 6 using grouping and write the expression in standard form. Standard form is just in decreasing degree of each term. So let's go ahead and do our side work over here. We have x plus 2 times x plus 6. And we distribute by taking our first number, multiplying it by everything in the second binomial. And we take our second number and we multiply by everything in our second binomial. So x times x, x squared, x times 6, 6x. 2 times x plus 2x, and then, of course, plus 12. Combine like terms, so this is x squared plus 8x plus 12. And that should give us our answer. Here we go. We got our correct answer. So, moving on down here, we're going to see drag the correct tiles onto the table. Not all tiles will be used, and we're supposed to simplify x minus 7, x minus 5 using the FOIL method. So this is one of those methods that they went over in the last section, but it basically follows what we just did. So let's go ahead and do this one using the FOIL method, which is going to look eerily similar, I promise. But let's set up our side work over here. So we have x minus 5. Okay, so then what is that going to be? That is going to be, we set up our FOIL method. FOIL, of course, stands for first, outside, inner, and last. So let's do our firsts. So x and x, that's going to give us x squared. If we multiply our outers, that's going to be multiplying x times negative 5. So that's going to be negative 5x. If we multiply our inners, that's going to be negative 7 times x, negative 7x. And if you multiply our lasts, that is going to be our negative 7 times negative 5, so plus 35. And wait a minute, I think I just multiplied the first term by everything in the other binomial, and the second term by everything in the other binomial. Go ahead and rewind the video if you want to verify that, but it's the exact same method, it just has a different name, same method, different hat. So if we are supposed to put in our first, outer, inner, and last results, the first one is going to be our x squared, negative 5x, negative 7x, here we go, and lastly we got 35. And our resulting simplified expression is negative 5x minus 7x is going to be x squared minus 12x plus 35, and of course we got it right. So on page 15, we are looking at the different forms of a quadratic expression. One being its standard form, one being its factored form. So we've definitely seen examples where our factored form can become our standard form. That's our whole us distributing and multiplying by polynomials. But we haven't gone over how a standard form can become our factored form. And in math, nearly everything, and for algebra, I'll just say everything is reversible. If you learn how to change one form into another, you definitely should be aware that the reverse is also possible. And that's what we're going to be learning here. And that's what it illustrates here. It says that this quadratic expression can be factored into two binomials again. How, you ask? Well, we're going to go over the method in just a bit. So page 16 is just a knowledge check. Which expressions represent a quadratic in its factored form? The factored form of a quadratic is, generally speaking, two polynomial or two binomials. So it's going to be 1, 2, and 3. Excuse me, it is not going to be 3 because there is a plus between these two. So it's not factored because they're not separated via multiplication, or they're not linked by multiplication. When you have a polynomial in its or specific quadratic and factored form, it should be two polynomials that are being multiplied by one another. So submit, and we absolutely got it correct. So page 18 goes over how to factor an expression, a polynomial. So the whole idea is to find out what the greatest common factor is, which may be a little intimidating at first, but the idea is that you're supposed to look for a common factor, and with practice, you will be able to identify the greatest common factor. But the example they give is that 8 plus 2x, you could recognize that both of them are multiples of 2, so that means the greatest factor for both terms is 2. So you take out a 2 and you just write what's left over inside the parentheses. And then, of course, you could do the reverse to check your answer. Let's go over another example and say that we had 7x minus 35. Well, these are both multiples of 7. So I could very much highlight that by separating them like this, where it turns into 7 times x minus 7 times 5, which, if I remove a 7 and put this on the outside of our parentheses, that is going to be x minus 5. So I identified a factor that is shared by both, and I took it out, and we got our factored form. On our next page, we're given an example 6t minus 15t squared. So once again, I'm going to look at what these two have in common. And I could recognize that these are both multiples of 3. 3 times 2t minus, excuse me, not 5, I want to keep things in order, minus 3 times 5t squared. So if I take out a 3, that means that I am left with 2t minus 5t squared. So I factored out a 3. However, if we keep looking at this expression, then you might notice they both have t. They're both t terms. So this is also a multiple of t, because this could be rewritten as just specifically this part. It can be rewritten as t times 2 minus t times 5t. And of course, the 3 drops. So I could take out another t. So 3t times 2 minus 5t is our fully factored form. Now, you may ask why I didn't take out both t's from our second term, from our t squared term. Well, that's because our first term only had one t. So that's also what it means by its greatest common factor. You can't just take out whatever you want. You need to make sure that whatever you take out is shared by whatever you are factoring. So that is why that 6t minus 15t squared, you can only take out a 3t and nothing more. So this is our fully factored form. Eventually, you might be able to recognize that this is the greatest factor just from the start, and you don't have to break it out into multiple steps. But just starting out, just factor step by step, and you will eventually discover this. You will discover your greatest common factor. So that's all displayed here, and let's give another example. Let's say that we had, excuse me, random mark. Let's say that I had 3xy squared plus 12x squared y. Okay, so 3 and 12 are both definitely factors, multiples of 3, so I could factor out a 3. Both of them share an x, so I could take out an x, and both of them share a y, so I could take out a y here. So that's how you would do it when you're more comfortable. You would be able to identify all those parts at once. So take your time on this, see how I got this as a factor. But what you're left with on the inside will be y, because you took out a 3 and an x from our first term, plus 4x, because I took out a 3 and a y from our second term, and an x. That's why we reduced the powers on both of these. Took out a y from our first term and an x from our second term. So if you're comfortable with that and able to follow along, let us continue. Okay, so on page 20, we're hit with a question. Factor the expression by finding the greatest common factor, and we're given our expression here. So let me rewrite it so we could work on this. That's going to be 16m squared minus 12m. So it may not be super obvious at first glance what they have in common, but let's go ahead and just take it step by step. They're both even numbers, so I could definitely take out a 2, and then what I'm left over with is 16 divided by 2 is going to be 8. Then, of course, the m squared minus 6m. Once again, they're even, so I know I could take out another 2, and that being 4m squared minus 3m. So that means I was able to take out 2 2's. 2 times 2 is going to be 4. So I know that's going to be a 4 that I took out in total. Now I look at the variables and I see that they have m in common. How many m's do they have in common? They only have one m, because their second term only has one m. So I cannot remove the 2 m's that are in this first term. I need to limit myself by seeing what they have in common, which is only one m. So I'm going to take out that m, and I'm left with 4m minus 3. And I do believe we find our answer here. There you go. So up until now, we've been factoring either binomials or parts of a polynomial. But what happens when we're trying to factor an entire quadratic, all 3 terms? Looking at it at face value, none of them have anything in common. But we definitely know that a quadratic could be written as a multiple of 2 binomials. So what gives? Well, what gives is that we need to understand the relationship between factoring a polynomial and multiplying 2 binomials. And the relationship is that you need to factor the first and last term of the quadratic, or the first and last term. Is that term or terms? Well, A and C, basically. You need to factor the first and last terms, I think it's terms, of the quadratic in such a way that when the factors are multiplied and added together, you get your middle term. So you need to factor the first and last term, I think it is just term, of the quadratic in such a way that when the factors are multiplied and added together, you get your middle term. So I very well could have just said that aloud, but this understanding of the process is very crucial. I would very much encourage you to add this to your notes. But what this means, if I take this example, is that I need to factor my 3x squared and factor my 7 in such a way that when I multiply and add them together, I get my middle term 2x. And the reason for that is, it'll illustrate on page 24, that when you FOIL, when you go from unfactored form to the standard form of quadratic, you have your first term, x times x, you get this, and you get p and q, those are the factors of your last term c. If you look, the way that you FOIL is that you multiply the factors of your first term, x and q, and add it to the remaining factors of your first and last term, that being p and x. So if you understand the method or look at the method, it seems, okay, we're able to reverse engineer this. So that's the reason why we need to factor in such a special way. So it may be confusing to wrap your head around at first, but the more examples you do, hopefully the more clear it will be. So let's try and jump into some of those examples. Okay, so we hit our next set of questions on page 27. And our first question is to rewrite the expression in factored form for x squared minus 10x plus 9. So let me set up my side work over here. I'm going to have x squared minus 10x plus 9, and I'm going to attempt to factor this quadratic. So the first thing I'm going to do is I'm going to set up my two parentheses. And now let's go ahead and do some side work over here as well. I'm going to look at my first term, and I'm going to look at my last term. So x squared and 9. So x squared, luckily enough, only has one way it could be factored, that being x times x. So I only have one option as to how to fill in my binomial, that being two x's in the front of each. 9, I have a couple of options, though not many. The factors over 9 are 9 times 1 and also 3 times 3. So let's go ahead and try 3 times 3. So the way that we check to see if our answer is correct is by multiplying our outer terms and our inner terms. We're doing the OI of the FOIL method in order to see. So x times 3 is 3x. 3 times x is 3x. We add these together and we get 6x, which is not our desired middle term. So this combination will not work. So we start over and we try another combination. So let's try R1 and R9. So again, we check by multiplying our outside terms and multiplying our in terms. X times 9 is 9x. 1 times x is x. Add these together and we get 10x, which is almost our desired term. The problem is we want negative x instead of positive x. So what can we do? Well, luckily for us, we know that a negative times a negative is equal to positive. So even though our number we're working with is positive 9, we could say that negative 1 times negative 9 is equal to positive 9. But what that lets us do is we could change our binomials into x minus 1 and x minus 9, making that negative x and negative 9, which when we add them together is negative 10. So we have found our factored form. So we have x minus 1 and x minus 9. Perfect. So if you had trouble following along with that, I very much encourage you to rewind the video, check out the last couple pages, and then re-examine this problem. But moving along, Part B, it says, when written in factored form, which two polynomials have a factor of x plus 12? Oh boy, so this is one question that is secretly 1, 2, 3, 4, 5 questions. So let's go ahead and do our work. We're going to see if we can speed run this a bit. So we're going to have x squared minus 12x plus 27. So again, x and x for all of these, our middle terms are going to be, or excuse me, our first terms are going to be x and x. So is x plus 12 going to be a factor? So in order for that to be a factor of the polynomial, that needs to be a factor of our last term. Is 12 a factor of our last term? Nope. So we can disregard our first choice. Now, 36 is a multiple of 12, so that one at least has potential. So we have x plus 15, or x squared plus 15x plus 36. Well, now the question is, can we get that to be 15? And I think we can. Because if we factor out 36, we would get 12, and we would get 3, which if you plug in plus 12 plus 3, you would end up getting 15x. So this one is going to be one of our correct answers. So we have 1, yes. Let's go and try this one. So now we have x squared plus 8x plus 12. So 12 is definitely a factor of 12, that being 12 times 1. Now we just need to see if it works for our quadratic. So that being plus 1 plus 12, that gives us 13x, which is not our desired middle number. So this one is not going to be, this quadratic is not going to have a factor of x plus 12. So it all needs to work. We need to have the potential of having a factor of 12, and it needs to actually work for the quadratic. So I'm going to leave the last two questions for you to figure out on your own. If you're having trouble with them, please go back and rewatch parts of the video. But now looking at part C, how do the signs of b and c in the standard form, x squared plus bx plus c, affect the signs of p and q in the factored form? Well, depending on what your middle number is, you could manipulate the signs for c. So there are a couple examples. So if we have something like x squared minus x plus 2, you could still make this work. Oh, actually, this is a good example of something that you can't make work. So this could only be x minus 1 minus 2, which would give you negative 3, or plus 1 plus 2, which would give you 3. So you would not be able to factor this because your signs do not let you get a negative x here. So when you have a negative middle term, that means that either both of these need to be negative, or if that's impossible, then that means that our last term needs to be negative, because now this will work, because I will be able to factor negative 2 into negative 2, can be rewritten as, or has the factors of negative 1 and 2, or more specifically for this question, 1 and negative 2. So then I could plug those in as plus 1, negative 2, giving me x minus 2, then x, giving me negative x, which is my desired middle term. So if the middle term is negative, that means that either both need to be negative or the last term needs to be negative. I'm not sure if that's exactly what they were going for, but that's something I would put. When b is negative, c is both positive, negative. Yeah, that's basically what we went over. So yeah, that works. So that is going to bring us to the end of this particular section, but we do have a big old part 2 to go over. Okay, so hope this was helpful and good luck with your practice and mastery test. I will see you guys for Factoring Polynomials Part 2 tutorial.